Alright, let's get started on our problems for today. So the first problem is house robber. This is LeetCode number 198, house robber. You are a professional robber planning to rob houses along a street. Each house has a certain amount of money, but the only constraint stopping you is that adjacent houses have security systems connected and will automatically contact the police if two adjacent houses were broken into on the same night. Given an integer array nums representing the amount of money of each house, return the maximum amount of money you can rob tonight without alerting the police. Okay? So, I recall doing this problem a while back, like back in January when I was doing a little bit more interview prep. And I believe that this is a dynamic programming problem from what I can recall. Let's see. So, assuming that this is a dynamic programming problem, and this is an O1 knapsack problem, at least an O1 knapsack-like problem, right? Then what can we say? Well, suppose that we had n houses to consider. At the nth house, we need to keep two things in mind. So we can rob the house and take the money if we did not rob the previous house, or we can skip the house and stay with our current amount. Let me think. So looking at this, looking at the basic example, or at least the first example, at house 1, we can choose between either taking the amount, so that would be 1, or not taking the money, which is 0. At the second house, since we've taken the money from the house before, we can only take from this house. If we did not take from the house before, we can take from this house and take 2. If we took from the first house and did not take from the second house, then we can take from the third house for a total of 4. If we did not take from the first house but took from the second house, then we cannot take from the third house, which gives us a value of 3. And if we took from the third house, we cannot take from the fourth house, and therefore our value is 4. And if we did not take from, or if we did take from the third house, sorry, if we did not take from the first house, we took from the second house, then we cannot take from the third house, so this is still 2. But now we can take from the fourth house, which turns our total to 3. And in this case, essentially, we need 2, but do we only need 2? Do we only need 2 arrays? One that alternates between one and the other that alternates between the other. Well, let's see. Looking at the length that we're given, the constraint is that the problem has an input size of 100, which means that an O of n squared algorithm is probably what they're looking for, with 100 squared being 10,000. So that seems to allude to the fact that we probably need to be a little bit more careful with how we determine the houses that we rob. It's not just we alternate between 1, 3, 5. Because I could imagine a scenario where maybe we do 1, 2, 3, 4, 1. Yeah, 1, 2, 3, 4, and 1. Right? And if we just did that same thing, where we rob this house, we don't rob this house, we rob this house, we don't rob this house, and then we don't rob this house, and then we rob that house with nothing inside, compared to if we don't rob 1, rob 2, don't rob this. Okay, maybe it works for this one too. What I'm thinking is maybe if we do this, we did this, we did this, then it doesn't make sense. So 10340. So the idea is that we want to rob 1, then we want to rob 4. So we can't just take the odds versus evens choice. So how can instead we interpret it differently? Well, we can decide to rob 1, and we can decide not to rob 1. And if we rob 1, we cannot rob 2, but we can also decide to rob 2. And if we decide not to rob 2, then we have 2 choices to rob 3 or not, then 2 choices to rob 4 or not, and so on and so forth. Let me think. I think it might be easier if I identify the actual subproblem that we're trying to solve. So I think we want to choose the max between, and this is assuming t of n is our function. So it's max of t of n minus 2 plus nums of n. So either start, so if we want to rob 4, we choose the max of these two plus our current amount, because obviously we cannot rob 3, right? So it's a max of these, the previous, starting from the previous second, or it's t of n minus 1. So those are our two sort of, I think, our subproblems. We choose between either taking now and getting the max of the previous, or we get the previous max. What if we did turn it into a 2D array where we had the indices along here, and essentially what we do is that when we are at that specific house, that's basically assuming that we rob a given house. Well, if we rob this house, then we can't do t of n minus 2 because there is no t of n minus 2 here. So we stick with 1. Here we can do t of n minus 2, which is 1, plus 3, which works out, and that's 4. Here, if we do t of n minus 1, or t of n minus 2 plus 4, then that would get us 5. And here, t of n minus 2 is 4 plus 0, that's 4, which is less than 5, so we go with 5. If we decided to rob u, we would decide to rob u, then we can't rob, well, we can rob 3 and t of n minus 1, or t of n minus 2 in that case, which is, so I think this would propagate down. And essentially we would be saying, okay, like what would be the value if we robbed the house at each, but we also take the maximum from above? So in this case, for this iteration, we would get the ones filled in here. And this would propagate from the top. This 3 would be saying, okay, do I take 1 or do I take this value, which is rob the first house and rob this house, which is 4. Well, we're going to take that 4. Same thing here, this 5 and this 5 is going to propagate down. And so on and so forth, right? So the O of n squared happens not within the context of a 2D array, but within the context of a nested for loop, where we are checking that if we start by so we start by robbing the first house, and then we check the maximum of what we can get if we rob the first house. And then we check the maximum starting from robbing the second house, then the third house, and the fourth house, and so on and so forth. And of course, that produces a nested for loop that produces an n minus 1, n minus 2 iterations until n times n minus 1 over 2, which is an O of n squared algorithm. In this case, so that would be O of n squared runtime and O of n space, because we're using a one-dimensional array, we are just taking the maximum of whatever exists here compared to what exists before, as well as what exists 2 blocks down, as long as it exists, right? So let's go ahead and start coding this. So let's do a val. We'll say money earned is an int array of size nums dot size. We can say nums for each we'll do for each indexed, and then we'll do nums for I in index to nums.size minus 1. So it's inclusive. So this is our nested for loop. So we'll start by saying our value at money earned at this index is equal to the maximum of, and I think this max of takes in a variable number of inputs. Max of, I don't want Kotlin text, I want Kotlin sequences. No, maybe not Kotlin sequences. Is it Kotlin collections? I wonder if I could do max of 3 values natively without having to do some weird shenanigans. We'll see. Actually, what we will say is that if I minus 2 is greater than or equal to 0, then we can do that. Then we can say money earned is equal to max of, we can do nums, or not nums, money earned at I minus 2 plus our current index, or our current index as it stands right, or before, right? Otherwise, what we will say is that our money earned is equal to max of our current amount, or our previous amount, or our current amount. Hold on one second. Okay, maybe we can try something a little bit different. Let's see. For initialization, I think we can say we want our value to be, with a given index, we want it to be just equal to our nums at index. So we start off by just creating an array of, so it would be like, our array would start off as 1, 0, 3, 4, 0. Then on the first iteration, for, let's see, 1, 1, let's see, because this, Well, we first want to check if I mod 2 is equal to 0. Then we can rob the house, right? And I minus 2 is greater than or equal to 0. Or not I mod 2. We want index let me think. So in this case, we can either choose to rob this house and take the previous I minus 2, right? Okay, so we don't need that. Or in that case, we either choose between what already exists there or what exists before. So this is money earned I minus 1, or 0, which is money earned at I. Here at 3, we can choose to take the I minus 2 plus 3. Or we can choose the 1 from before. At 4, we can choose the I minus 2, which is the 1. Because this 1 is the optimal value if we were looking only at 1 and 0. And then at 4, we can take this 1 right here, add 4, so we have an optimal value of 5. And then here, we're going to take either the 4 or the 5, and of course we're going to take the 5. And then let me think. So now this doesn't change. So this is the initialization. This is the first iteration. This is second iteration. Well, the 0 doesn't change here. Three. The 3 will look at this one. There's 3. So that won't change. This will look at the 1 and 4 and not change. And so on and so forth. So this doesn't really change after the second iteration, does it? But is there a situation where it would? Let me test it out with other data sets. So let's do the 1, 2, 3, and 1. So that starts off like that. Then we take this. This is still less. So we just keep the original. This, you take that, so you do that. And this, you take that, so you take that. Because it's 3 versus 4. And you just take that. I wonder if you really need multiple iterations. I mean, I assume that you probably do. It's probably some edge case, which I have not considered. Money earned at nums.size minus 1. And we can say that if nums.size is equal to 1, we just return nums at 0, because that's the minimum within the constraint of this problem. Let's go ahead and run this, and let's see where we're at. Money earned, we want our money earned at I. Whoops. Let's see. Hmm. We want to make sure that that's greater than or equal to 0. Let's see. And otherwise, if we're at the beginning here, we've already assigned it to take that amount, so I don't think we need to change that. Let's go ahead and run through the other test case as well. Let's go ahead and toss a submit. Slow. Surprisingly slow. Maybe we don't need to do this. We don't need to index it all. If we didn't index that, if we did that instead, I don't think that changes much. Ooh, looks like we got the wrong answer too. Because the idea is that maybe we just don't want to index into the nums array like that. Perhaps initialization doesn't take that much time, take as much runtime. Let's see. 1 and 2. Our output is 1 and we expected 2. Started from 1. Then we walk through starting at 1. That answered there as 1 at the beginning. Then we move on to 2. 2 will just go inclusive, so it's at itself. And I minus 1 is greater than or equal to 0. And since that's not there anymore, then we either take, if we're at the second value, then we want to either take our current value or take the previous. Because there is no take second to previous, we either take the previous or we take our own. So I think this works. Let's just run it against our test suite. And then watch as this is not even faster than the previous submission. Oh, I click submit. Whoops. Well, this will be a good stress test. Yeah, it's about the same. In any case, it runs in O of n squared time, so asymptotically, I don't think it matters that much. In any case, I hope you learned something. So this is a dynamic programming approach to house robber, where we calculate the optimal solution at each step, and we go over all the steps in a nested manner in order to calculate our optimal solution at the end. So we break it down into subproblems where we can choose between a maximum of taking our item and getting the maximum of the 1 second to the previous. So the previous of the previous, because that's the next possible house that we could rob. So we want to get the optimal solution at that point. or we can simply choose to take the optimal solution that we've had starting from our previous. Whichever one is higher, that would be our optimal solution at our current house, essentially. In any case, I hope you learned something, and I'll see you for the next problem.